All right, we're talking about water and macromolecules. Yeah. Yeah, just grab the fast. All right, so we're going to start with water. And just to review, remember water is, what's the formula? H2O. It's an oxygen and two hydrogens. They kind of come off at an angle like that, yeah? Oh, macromolecules. I'll write it again later. But it's MACRO molecules. And recall, oxygen has these covalent bonds. They're sharing electrons, but do they share evenly? No, oxygen's a bully. It sucks up the electrons, so this end of the atom is, or this end of the molecule is negative. This end is positive. Same deal here. These guys are positive. So within the molecule itself, there's a negative side and a positive side. That means water is an example of a polar molecule. Just like how Earth has two poles, right? We have a North Pole and a South Pole. There's actually like a positive magnetic and a negative magnetic end to the Earth. These molecules have positive and negative ends. To contrast this, we'll choose a molecule that's nonpolar. And our classic example in biology are all the carbon and hydrogen based ones. So we'll pick the simplest one. Somebody made this the other day. This is methane. And the whole point with methane is it is nonpolar. Why is it nonpolar? Well, carbon actually plays really nicely with hydrogen. It's still a fifth grader, but it gets along really, really well with these kindergartners. And instead of stealing the electron and keeping it all the time, it shares very equally. So carbon doesn't have any extra negative charge. The hydrogen doesn't have any extra positive charge. It's just a very neutral, non-polar molecule. The reason why water and oil don't mix is because water is very polar. Oil is very non-polar, yeah. Another fact about water, use blue, sure, why not? Water, right up there, is a very good solvent. Very good, actually. One of the very best out there. What's a solvent? I'm sure you guys know. Feel free to suggest it. What do solvents do? Yeah, close. Melt, or what happens if you take, like, I don't know, yeah, dissolve. Exactly. So solvent, we're going to find that, they dissolve solutes, yeah. Yeah, lots and lots of stuff dissolves in water. So we had the other day sodium, Na+, right? And then we also had chloride with this Cl-. What are these charged molecules called? Remember what's a charged molecule called? This guy's short an electron, so he's positive, and therefore he's called a what? Ion, yes, these are ions, right? These ions, such as sodium chloride, as a solid, right, as a dry solid, they form crystals. But when you put them in water, what happens when you put salt in water? It dissolves. Yeah, what's literally happening is the oxygen is the negative end, right? I should have drawn a little closer. There we go. The oxygen is hanging out around this sodium because the oxygen ends are all negative, 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 negative. You get all these water molecules that go and hang around that one sodium ion. And then it's free to kind of float around the rest of the water by itself. Same deal with chlorine here. But it'd be the hydrogen end. The water will surround it. The individual chlorine atoms are breaking off, getting surrounded by water, and then going and floating off in the water. This is why you can see the salt crystals in the bottom of your water, but then you stir it up, and can you see the salt anymore once it dissolves? No, because the individual atoms are being completely surrounded by the water and separated out. Water can dissolve with other stuff too. Like, for example, sugar. Sugar is a much bigger molecule. It's got what, like a carbon, 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 carbon. We'll draw this again later, so don't worry about it. Carbon, oxygen, carbon, and then a bunch of like other things over here. Anyway, point is, it's this big complicated molecule. Water can surround this thing too. You get water. Even though the sugar molecule is way bigger than the water, enough water can surround it, it can break it off as a little chunk, and then that sugar molecule can go and float off all by itself and just hang out floating around in the water. So water is really good at dissolving stuff, molecule by molecule. Obviously, not everything dissolves, but a lot of stuff does. This means it's really good for like cleaning stuff up, right? My wife spilled some honey on the floor last night. She used just like a wet rag and water, right, to clean it up, because you're able to dissolve all that sugar up with the water. When you got like dirt on the kitchen table or whatever, you'll wipe it up with water or something with water. Okay, the other thing about water is it can break apart. Let's draw. Oxygen here, here's its little hydrogens, and it does this spontaneously. Sometimes this bond here to the other hydrogen swaps over. That little hydrogen bond that used to be connected to this guy over here, it actually becomes a real covalent bond. And this becomes hydrogen. It's possible, it's not super stable, but it's totally possible for oxygen to make an extra bond here. When it does, it becomes an ion. Same deal with this thing. It can lose this hydrogen, and then it becomes -1 charge. This extra hydrogen is our version of an acid. An acid is some sort of molecule that has an extra hydrogen that wants to donate somewhere. This thing really wants a hydrogen and will take hydrogen from other molecules. What is it called? If you're not an acid, you're a base, yeah. Those of you that have taken like the rudimentary chemistry stuff, remember, sorry. Yell at me if you can't see the label. You got acids and bases. Water makes its own acid and base. It just randomly will swap hydrogens across sometimes to make a slight temporary base and a temporary acid.
So does it swap between more acidic and more basic? Just whenever it wants?
The individual molecules, right? But this base is right next to this acid. So they cancel each other out. They're always constantly, it's the same number of hydrogen around anyway. But the point is, water is constantly a little bit acidic and a little bit basic. And it does matter, actually. Because water can act as a base sometimes, it can act as an acid other times. But it's super, super weak as both. And in fact, it'd just be considered neutral. This is where, it's a I don't remember the numbers, but it's like a 1 in a million or 1 in a billion shot or something. A tiny, tiny fraction of these water molecules will do this, and it's usually temporary. They'll go back to being normal right away. But, however, it does happen. And that brings us to this scale here, right in the middle. The frequency at which this happens, I don't remember off the top of my head like the actual conversion, but we're going to put it as a 7. If you have some sort of substance that has 10 times the amount of acid in it than water, we're going to put that here on the scale as 6. If it's 10 times stronger than that, if it's 100 times stronger than water, we're going to put it as 5. If it's 1,000 times, we'll put it as 4. If it's 10,000 times, we'll put it as 3. 100,000 times 2. If it's 1,000,000 times stronger than water, we're going to put it as a 1. Same deal with the base. If we have 10 times more base or 10 times less acid, we're going to call that 8, 9, 10, 11, 12, 13, on up to 14. So there's this theoretical range between 0 and 14. What's this scale called? Oh, come on, you guys do this every time you like test your fish tank or something. You're testing like the pH, right? The pH scale, yep. This is neutral. These are strong bases. These are strong acids. So strong acids would be like 2 or 3. Strong bases would be like 10, 11, 12. A weak acid would be something like 6.2 or something like that on the pH scale. A weak base, 7.5, something like that. It's really important to track the pH of like living systems because there's a tolerance for pH in most living things, right? What would happen if your blood became too acidic?
Die.
Yeah, you die. You straight up die. In fact, do you know what the pH of blood is? It's not exactly 7. Yeah, it's actually slightly basic. Some people didn't realize that. They think humans have acidic blood. We don't. Most of our cells, though, actually are slightly acidic. It's like 6.7 or something like that. Most of our blood is 7.2. So within the cell, we want a little bit of acid. In our blood, it's a little bit basic. And then there's a tolerance. Every single cell, every single protein has a perfect tolerance that it really likes. When you get an acid burn, right? If I were to get acid spilled on my body and I'd get a burn, what is it doing? Well, it's actually destroying the proteins. So it's super important that living systems like maintain a good acid balance. And one of the ways to maintain that acid balance is using a thing called a buffer. What are buffers? What's a buffer in like the regular world?
Something stops something else.
It stops something else? Were you gonna add something? Yeah, they're like barriers or like regions that, I don't know, like watching a volleyball game the other day, right? There's a buffer zone outside of the court where they're allowed to like run and hit the ball back in, right? It's not like in the court, but it's this buffer zone, right? Same deal with acids and bases. There are some compounds that form buffers that resist change. Or prevent change. So they protect whatever pH level you're trying to stay at. If you really need your blood to be 7.2 to stay alive, you have buffers in your blood that if I add a little bit of acid, it'll neutralize the acid. If I add a little bit of base, it'll neutralize the base. It resists the change and it'll keep it really stable. Okay, a couple more things about water and why water is so awesome. All right, we already talked about how it's a good solvent. It's polar, et cetera, et cetera. Water is also really good at absorbing heat. Because of all those hydrogen bonds between the hydrogen of one water molecule and the oxygen of the other, it can takes tons and tons of energy before the bonds are broken, before it can evaporate, right? December in Fairbanks could be 40 below. Is it gonna be 40 below in Anchorage? No, why not? It's because they're on the ocean. The ocean is full of water, right? And it resists changes to temperature because it not only absorbs heat, right? But it also like absorbs cold, I guess, in that same sense. So it releases the heat from the summer all winter long there in Anchorage. So it resists. Yeah, when you're on the coastal place, because you're near the water, you just don't have as many changes to temperature. Water also has really good cohesion and really good adhesion. Cohesion is the ability for water molecules to stick to themselves. Go ahead and add that definition if you don't know it. Adhesion is the ability for water molecules to stick to other stuff. Right, so when you finish a drink, right, finish your Powerade, there in the bottom of the Powerade is a little bit of water droplets. Why? Because it's adhering to the plastic. And then water is the ability for it to just clump up as like a single raindrop. It falls as drops, not as just mist all the time, right? One more property of water, super important for life on Earth. It has to do with the density. What happens when things get colder? What happens to their density usually? They get more dense. Yeah, this is true of air, right? If the air is colder, it's more dense. This is why hot air balloons rise, right? You heat it up, it becomes less dense, it floats, hot air balloons go up. Water is one of the few things, when it freezes, becomes less dense. It's really weird. Again, because of those hydrogen bonds, it locks in crystal in place, and it is slightly less dense as an ice than it was as water, right? So the solid is less dense than the liquid. What? Yeah, that's how it expands. And it'll float, right? So it's theorized if ice sank, the oceans would just be like solid ice. Like after the first 100 meters or whatever, it'd just be solid ice at the bottom of the oceans. All the lakes would freeze solid, bottom to top. Nothing would be able to live. But because it starts top to bottom, it insulates it. You get all these fish that can hang out in the lakes and stuff. So super important for life on Earth is the fact that water floats. Yay. All right, now we're gonna go into some molecule stuff. And my apologies, I know some of it's pretty technical, but I wanna see if you guys know the 4 most common elements in the body. What are the 4 most common elements in the human body? What was it? Oxygen is one of them, yeah. Right there, bam. Yeah. Carbon dioxide is not an element. Wait, hold on.
I had it, but it's gone.
Nitrogen, yes, nitrogen's one of them. In fact, nitrogen's the hard one. It should be the last one you guys got. The other 2 are more common. What was it? Hydrogen, excellent. And there's one more.
Carbon?
Yeah, carbon. Yeah, and I drew the symbol or the little 1 or 2 letter code, which they all have. Hydrogen, oxygen, nitrogen, carbon. If you don't know them, write them out. Here's the handy thing about this. If you go back to your periodic table, remember how we were talking about hydrogen and how many bonds it can form because of its electrons? How many electrons does hydrogen have? 1, right? How many does it want to have in its outer shell? 2. So how many bonds can it easily form? Yeah, it likes to form a bond. If it can share a bond, then it gets 2 electrons. So hydrogen can easily make 1 bond. Oxygen has how many electrons? 8, right? How many are on the inner orbital? 2. How many are on the next orbital? 6. How many does it want to have? 8. So it needs how many more? 2. So it can form 2 more bonds pretty easily. In fact, that's its natural state, is to have 2 bonds. How many bonds do you think nitrogen can make? 3. Because it has 5 electrons in its outer orbital. It's missing 3. It can make 3 bonds. How many does carbon make? 4. Yeah. 3. This is our little cheat sheet when we're making molecules. Just like when you're making a molecule with the little models, when we're drawing out molecules, you can make sure that everything has the right number of bonds. This guy here has 1, 2, 3, 4 bonds, therefore it is carbon. Yep. This guy here has 1 bond, therefore it's hydrogen. This one here has how many bonds? What element is it? Nitrogen. Yeah, it has 3 bonds, it's nitrogen. The green were like, I think heavy hydrogen or something. I don't know. There might be other elements that can make 1 bond, but what was that?
Other elements.
Yeah, other elements that can make 1 bond would be like these guys here.
Yeah.
So it could be fluorine or chlorine or something, bromine. Yeah. I don't know. Probably depends on what you're using it for. Okay, so let's draw a molecule. Somebody made me this molecule in one of my periods. This is meth.
That was great.
Actually, I think it was 3rd period. Anyway, somebody made me meth. We're going to draw meth because it's I don't know, it's kind of a cool molecule. Not super big. It's about the right size for what we want to do. Let me zoom this out. Okay. So if we're going to draw meth here, first thing is let's draw this part. It's pretty unique, right? It's how many carbons? 6 arranged how? In a ring, in a hexagon ring. So let's go ahead and draw that. So we're going to draw carbon, 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 carbon. Okay. What else do you know about what's going on here? What's this?
The carbon is connecting to the carbon.
Yeah, but not just once. Twice. It's a double bond, right? You see these double bonds? Yeah, so we're going to draw that in as well. So let's see, we're going to do that a double bond, this one a double bond, and this one a double bond. Okay, and then we can't forget this guy here. What's this one? Hydrogen. What's this one? Yeah, so notice each one of these carbons here all has 1 hydrogen, with the exception of that guy. So I'm going to draw hydrogen, 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 hydrogen. Okay, are we doing all right? Okay, does that bring me to 4 bonds for this carbon? Yeah, I got 4 bonds here, 4 bonds here, 4 bonds here, 4 bonds here, 1, 1, 1, 1, 1. The only one that doesn't have 4 bonds is this carbon, which represents this guy. So what else is this carbon bonded to? Another carbon, yeah. So I'm going to go up for this carbon. Don't worry too much about the angles. What's this carbon bonded to?
Helium and another carbon.
A what?
2 helium, or not helium.
2 hydrogen and 1 carbon, yeah. So you're going to draw those hydrogens. And then another carbon. Okay, that's this carbon here. What's this carbon bonded to? This guy's bonded to 3 different things. A nitrogen. Can you see? Oh, carbon. What's that thing? Hydrogen and carbon. Yep. Up for carbon, down for nitrogen, hydrogen. Okay, I guess I'll finish off this carbon. What's attached to that carbon? A little hard to see. What's attached to this carbon? How many? 3. 3 hydrogens. 1, 2, 3. And then the nitrogen, what's attached to the nitrogen?
Carbon.
1 carbon and yep. hydrogen, carbon. Again, don't worry about the angles you draw it at. And then the final carbon has 3 more hydrogens. Hopefully, you have something that looks kind of like this. All right, we've just drawn meth. Methamphetamine. Don't do drugs, by the way.
Tell us how to cook it.
Or if you do drugs, don't do meth.
Tell us how to cook it now. How do you make it? Theoretically speaking. Theoretically speaking, what would you use?
I had organic chemistry professor that like would talk about drugs all the time and like all the different reactions to make them. And he's like, this one's called crank because you'd store it in your crankcase in your motorcycle. He was a weird dude. All right. So this is one way. I want us to be able to just recognize a molecule when we see it, be like, oh, this is, carbons and hydrogens, and this is a chain thing. That's all I really want us to get out of this. The other thing I want to focus on is the fact this was a pain to draw. There's a shortcut method to drawing a molecule. Organic molecules, at least. So organic molecules can often be drawn with the assumption that there's going to be lots of carbon in it. So you can draw this molecule without even drawing the carbon. You're going to leave out the carbons. You can also put the assumption in. Remember how before when you guys had like a hole or something, I was like, hey, you can't have an empty hole. What do you plug in there to just get rid of the hole? You'd put a hydrogen, because if you put anything else, there would just be more holes and more bonds you'd have to make, right? So if you're just trying to like close it off and finish it, you'd put a hydrogen. We can make the assumption that there's a hydrogen everywhere it's possible to put a hydrogen. So if we make those two assumptions, this is how we're going to draw the ring. It's going to be a double bond, a single bond, double bond, single bond, double bond, single bond. Carbons are implied, hydrogens are implied. It goes out to a carbon, and then I'm going to make this little kink like that for that carbon, a kink like that for that carbon. I'm going to have to draw the nitrogen. And then finally, one more carbon's out there. I'm done. I don't have to draw the hydrogens. It's implied that there's a carbon here at the corner and 2 hydrogens poking off of it. It's implied that there's a carbon here and 1 hydrogen poking off of it, because I have 3 bonds, 1 left.
How would you write that? Would it be? Couldn't you just gotta count how many there is?
No, you just draw this. This is a valid picture of a molecule, just like this. Like, so the naming conventions are complex. Each part has its own like name, right? And then you number the carbons. So you'd have like it's called like a benzene ring. So it'd be like benzo, 1, 2, 3, 4, 5, 6, 6 benzo ethyl nitro methylate, or something like that is the official name. So you just name it part by part by part, string them all together. Anyway, you guys see how these are the same thing? You are responsible for recognizing all of organic molecules, both drawn like this and like this. They're the same thing. What was that? Sure. We'll do more examples. We'll practice and stuff too. Okay, this brings us to our big macromolecule section. We're back in? Yeah, we're back in. Okay, macromolecules. What does macro mean?
Big.
Macro means big, yes. It's a little confusing because those of you that do photography use a macro lens to take pictures of small things. But I think that has more to do with like the angle or the field of view or the aperture or something like that, which would be really big. Macro means big. Furthermore, all of these organic molecules are going to have 2 parts. They're going to have a monomer and a polymer. What does mono mean? One. What does poly mean? Multiple. Yeah. So the way you get macromolecules, these giant molecules, some of these molecules, single molecules are just absolutely huge. just millions and billions of like individual atoms all clumped together as a single molecule. So the way we get these giant macromolecules is we take a subunit and we put them together like Legos to make these polymers. And we'll start with carbohydrates. I guess they're green. Carbohydrates is our class. A classic monomer of carbohydrates would be sugar. And we can go ahead and draw sugar. Sugar is a little chain of carbons. Oxygen. It's something like this. There's actually more oxygens too. Maybe like an oxygen here, oxygen here, oxygen here, oxygen here, oxygen there. So sugars, the formula for sugar, glucose is C6H12O6. It's going to come up time and again. It's our basic building block, sugar. Okay, so that's our simple sugar. What's a more complex carbohydrate? What was that? Glucose. Glucose is actually really simple. This is glucose, the one I've drawn. Sucrose is slightly different. Sucrose is actually two carbohydrates put together. It's called a dimer, or a dimer, something like that. This would be sucrose, which I think is fructose plus dextrose. Anyway, there's a slightly different name for each like little tiny change in the molecular formula. But sucrose is two sugar molecules put together, basically. Still pretty simple. There are more complex carbohydrates. What are they? Like what's in pasta and bread? What? Gluten is one, actually. Gluten is a carbohydrate. But the one I was thinking of was starch. I'll put them both down. Starch, gluten. Fiber that we can't digest that's really common in plants is cellulose. What was that? Is it in corn? Yeah, corn has all of these, I think. Well, not gluten, but starch and cellulose. But most of these are little daisy chains of sugar molecules. Sometimes they branch off, right? Sometimes they don't branch off. Sometimes they have other things in between or different structures or shapes or whatever. Each one is slightly different, but they're all made of monomers of sugar. Lignin's another one. The tree wood is just carbohydrates all put together. Glycogen in the body is a complex carbohydrate. It's a polymer. Cool. Next one are lipids. Red, I'll keep it up. Lipids have a monomer. What is a lipid anyway? You eat lipids all the time, especially at McDonald's and stuff. What are lipids? Fat. Yeah, lipids are fats. Are fats water soluble? No. Lipids are like waxes, oils, fats. They are non-polar. So the monomer of a lipid is called a fatty acid. And it looks like this. It has this big long chain Carbon, 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 carbon. What are the other two elements off this carbon that I didn't draw? Hydrogen. Yeah, there's 2 hydrogens off each little corner here. Carbon, 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 carbon. When I get to the end, the fatty acid has a carbon, double bonded to an oxygen, another oxygen, and then hydrogen. This is a fatty acid because it likes to donate this hydrogen to you. The most common version polymer in your body, if it wants to send fat around, is called a triglyceride. You have these chains of different lengths. They actually form onto this like sugar molecule type thing. But it's, what does tri mean? 3. Yeah, it's 3 fatty acids put together to make a triglyceride. When your body wants to send fat around the body for energy reasons or storage reasons or whatever, it forms triglycerides and then puts it into your blood. In fact, now would be a good time to talk about like why some fats clog up your coronary artery and why some are better and healthier for you. All right, so what's the unhealthy type of fat? Saturated fat, yeah. What makes it saturated, what the word saturated means, is it means that this hydrocarbon chain is saturated with hydrogen. So every single one, badoom, 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 has another carbon at one end, and then the rest is just hydrogen. So it makes this actually regular pattern. So saturated fat is just up, down, up, down, up, down, up, down, up, down. The thing is, it makes these nice straight, overall the molecule is nice and straight, right? And in fact, your body can pack them in really tight because they fit really well, just, okay? This means that they are more likely to become a solid, right? This is why people make saturated fats. They want, oh, we want to make margarine. You take vegetable oil, you jam a bunch of hydrogen into it, you saturate all these bonds, and they become nice and straight, and now they're solid at room temperature, which means they're more likely to be solid in your arteries. So that's a saturated one. The unsaturated means that in some places it's missing the hydrogen that goes here, right? So instead of making a bond with more hydrogen, carbon ends up making these double bonds. And it'll go kink, it'll go up, down, up, down, up, down like this, and then all of a sudden there'll be a double bond, and that forms a kink in the chain. And then it'll go like this, in some other direction. It'll form a double bond, and then, you know, so the unsaturated fat molecules, do they clump together nice and tight? No, they're more likely to be loose and flowing. So these are the ones that won't clog your arteries, or the olive oils of the world. One more super important fat type thing, or lipid, we gotta cover is called a phospholipid. What does phospho mean? It's just an element. What element? What element? Does anyone know what the P represents here? Element called phosphorus. Hopefully you've heard of phosphorus before. This phosphorus is bound to a bunch of oxygens. It's really, really polar. But it's also connected to a pair of lipids. Usually one of them kinks out a little bit. But yeah, a phospholipid is super important because it has a polar region and a non-polar. So the fatty part of a phospholipid is nonpolar. That means it like can dissolve in oil. The polar part can dissolve in what? Water, yeah. Phospholipids create these membranes that make life able to exist on Earth because they form these phospholipid bilayers, which are cell membranes, right? It's theorized that these phospholipids had to have existed before any sort of like anything considering life could really form. Okay, and every single one of our cells is just totally packed full of phospholipids. Also, like soap is pretty similar to phospholipids too. They have like a polar, non-polar end, that sort of thing. Good for getting rid of dirt and stuff. All right, last two. Next one is protein. Does anyone know what the monomer protein is called? The monomer protein is called an amino acid. Amino acids look like this. They have a central carbon. H right there. This side has a carboxyl group. C double bond into the double bond and H, right? We've seen that on fatty acids as well. Over on this side, we have a nitrogen. That's our amino acid. Oh, but wait, I made a mistake. There's one thing missing. What is it? One of the atoms I drew up there doesn't have enough bonds. Which one is it? Oxygen makes two. Which carbon? The middle carbon. Yeah, it has one more bond here. And it bonds to a surprise. There's no element called R. It's got its mystery group. There are 22 different options that R could be. It could be something simple like a hydrogen. It could be other elements. It could be a weird chain or a ring or something like that. There are 22 different amino acids, and they all just have a different thing right here. Everything else about the amino acids is the same. That means when we make our polymer, we bind these amino acids together. This end connects to this end on the other one, which they basically can just form together as a big long chain. Kind of like how usually when I leave people alone with these markers long enough, what do? No, some high school boys, they go like, oh, look at that. I can put this one to this one to this one to this one, right? Like, no, it's the same end. One end matches up with the other end, right? You can do the same thing with these polymers, with these amino acids to make a polymer. I'm just gonna draw them as like a little circle. You can attach this one to another one, to another one, to another one, to another one. You can put hundreds of these things together, and that'll make what's called a polypeptide. Or a protein. These polypeptides, I drew this as a string so you can see that there's like all these different amino acids here. Boop, 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 boop. But then that folds up, it folds up into usually some sort of functional thing. Remember how we were talking about enzymes earlier? Enzymes are proteins. This molecule here is a giant folding of just hundreds of different amino acids. It's just this chain that's just folded up into this weird little shape that does some sort of function for the body. Okay. And then finally, what determines this order of amino acids? Does anyone know? How does your body know what order to put these amino acids in? If only there was some sort of blueprint or code for it. What is it? What was that? Say it again. DNA. RNA. DNA stands for deoxyribonucleic acid. Here's the monomer. Monomer is what we'd call a nucleic acid. There's 3 parts to nucleic acid. The first part is the phosphate group. And then there's a sugar, 5-carbon sugar. And then there's a base. And the base can be a few different things. And just draw this as like a couple of rings with nitrogen in them. You're not really required to like memorize the individual ones and their names, but you do need to be able to recognize all of these molecules. You need to be able to recognize. If I show you a picture of them, you should be able to say, "Oh, that's a nucleic acid. That's a amino acid, whatever it is." This is the phosphate group. This is the sugar. In the case of RNA, it's ribose. In the case of DNA, it's deoxyribose. It's a ribose molecule without missing one of its oxygens. And then this part is the base. There are 4 different bases in DNA and 4 different bases in RNA. RNA has 1 base that's different than DNA. So really there's 5 potentially different bases. And then when we put them together as a polymer, we actually string the sugars and the phosphates together. So you have a sugar, and then it goes to a phosphate, and then another sugar, and then it goes to another, or a phosphate to the sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar. And this will form the classic backbone. Do you just have 1 strand of DNA? Yeah, you always have 2, yeah. Oh, and they're bound to each other. Make it look like a double helix. There we go. Ta-da. Thanks for finishing the notes. Have a good night.